All right, I think we are live now. Sorry about that. Please start the talk now.
Okay. Hello, everybody. I'm coming to you from down under. I'm in Canberra, Australia right now. And let's see. Let's go to the next slide. There we go. So I'm interested in cosmology. I got my PhD at Berkeley in 1994, and it was cosmology I was studying, but there's also something philosophical, really profoundly philosophical about cosmology. And I wanted to talk about that today. So if you're interested in cosmology, I can recommend this book. I have it right in front of me here. This was written by H.R. Harrison. It's called Cosmology, Science of the Universe. And there's a first edition and a second edition. And the reason I'm pointing this out is because it's kind of like an introductory textbook on cosmology, but it has a lot of philosophical content. And that's why it makes it approachable for people who are not studying astrophysics, but are even studying philosophy or history or humanities. All right, so E.R. Harrison. Now, so cosmophilosophy, I guess I've just made up this word, and I think of it as some philosophical and conceptual. Oh, I'm hearing a little bit of background.
I'm going to mute others. You can continue.
Okay.
Sorry about that.
Okay. Everybody's allowed to sneeze here. All right.
So please mute yourselves. I'll go to the list. I'm one as well. Yep, that's better.
Yes, I don't hear it anymore. It's screeching, all kinds of people. Okay, yeah. So I made up this word called cosmophilosophy. I've never seen it before, but it basically, I want to talk about the philosophical, conceptual weirdnesses of modern cosmology. So for example, there are questions like, what does it mean to say the universe is expanding? And is the universe infinite? And how can you have an origin from nothing? And so those are three, I guess, compartments that I want to divide my talk into. So, expansion of the universe. This is Edwin Hubble standing there with his fishing rod, and he's doing two things here that we don't do anymore. He's smoking in an observatory, and he's looking through a telescope, two things that astronomers no longer do. So, in the 1920s, 1929 approximately, he made this plot, and on the x-axis is distance, and the y-axis is velocity. And you can tell the velocity of an object by looking at the redshift. They have a spectral lines, and they get shifted, and they say, oh, that's because of the Doppler shift. And to make you more familiar with the Doppler shift, if you go to a race car, go to a race, you'll hear cars go by you like this, and that's the high frequency as they come towards you and the low frequency as they go away. The same thing happens to light. And so when the light from a galaxy is redshifted, it gets shifted from the normal place where it is to red and lower energies, just like. So this is a plot he made, and from this plot he said, oh look, it looks like there's a line here, and that line is the velocity here is equal to some constant times the distance, and that's Hubble's law. Velocity equals h times distance, or velocity of recession equals h times d. That's a very simple equation, and it's a very important equation. But I want to say that in the last, 80, 90 years, this data has been supplemented. This data in the green is now in this tiny, tiny green square there. Matter of fact, this green square is is about twice the size of this green square. So you can see this is in megaparsecs, and this is 20 megaparsecs, and here's 1 megaparsec, 2 megaparsecs. So this original data was a tiny, tiny fraction of the data we have today. And so we're very sure that this relationship holds. And this is called Hubble's law. So Hubble's law means recession velocity of these distant galaxies is equal to a constant times the distance. Now this has profound philosophical implications for an expanding universe. So one is that time has a beginning. Now, most people say, how can time have a beginning? That doesn't make any sense. Well, this is what it means. When you have an expanding universe, all you have to do is go backwards. It was tighter, and things were closer and closer and closer and closer. And the Big Bang is the extrapolation of the, the extrapolation of these velocities into the past. until a point where everything was on top of everything else. So time has a beginning, and our universe has an origin based on this expansion. Also, since telescopes are time machines, what that means is that when you look at things that are far away, you're looking into the past. You're looking into you're looking back in time. So, for example, excuse me, let me have a drink of water. When you look at the moon, the moon is about 400,000 kilometers away. Light travels at about 300,000 kilometers a second. So when you look at the moon tonight, you're looking at about 1.3 seconds into the past. If you look at the sun, you're looking about 8 minutes and 20 seconds into the past. If you were in Australia right now, you could see the closest star to the sun, which is Alpha Centauri, and it is about 4.2 light years away. And so you're looking 4 years into the past when you see that star. So that's the sense that which a telescope is a time machine. And the further we look, the further we can see into the past. And as we get closer to the beginning, the universe is smaller and hotter. So the universe is expanding. That means there was a big bang. That means the universe has a finite age. Now, I should point out that this is often difficult to understand because my father, for example, doesn't believe that it makes any sense to talk about the origin of time. How can time have a beginning? And but this is the implication of the expansion of the universe in the Big Bang. Another question we can ask is, if the universe is expanding, what is it expanding into? And this is, you can see diagrams like this. The universe is expanding. Here's the universe. It's getting bigger and bigger and bigger. Now, in general relativity, you do not need space outside the universe to expand into. The universe does not have a center. It does not have an edge, and it does not have space outside of it to expand into. Everything you know about has a center, like my head, for example, or this room, or the earth. And if it's expanding into the space around it. But the universe is all the space. And when it expands, it does not need space to expand into. So what that means for this diagram is that these areas here are just put in there by an artist. It's space into which the universe is expanding, but that means it's misleading. Do not take this too seriously. Now, also, the Big Bang was not an explosion. I know this because as a child, I would set off firecrackers, and explosions have centers. Explosions have high pressure on the inside and low pressure on the outside, and general relativity tells us that the pressure was the same everywhere. As a matter of fact, if you have more pressure, then you collapse because pressure is a type of energy that gravitates. So the Big Bang was not an explosion. It did not have a center. And so what that means, I've taken 3 pictures here from books about the Big Bang, and they're wrong. They imply that there's a center here or here or here. So I'm going to have to cut them out and say that is just misleading. And you can't point anywhere in the sky and say, oh, look, there was the Big Bang. There was the Big Bang. That is just silly. The Big Bang was everywhere. And I will try to explain what that means. So in 1992, we took this picture. This is a full sky map of the cosmic microwave background. These are the oldest photons you can see. And we discovered fluctuations. These are the hot spots and the cool spots, and the cool spots and the hot spots in this map. This is the galaxy. It's just foreground. You can ignore it. But the other things, this hot spot here and this cool spot here, are cool spots and hot spots from the surface of last scattering. And we discovered these in 1992 with the COBE DMR, differential microwave radiometer. And that's what I did my PhD on. And I got my PhD in 1994. So in 2006, John Mather here and George Smoot, my PhD supervisor, got the Nobel Prize in Physics for this discovery of fluctuations, and also the discovery of the temperature of this cosmic microwave background. So what is this microwave background? I should point out that think of this map as a full sky map. You take it and wrap it around your head so that everywhere you look, you see these blue and red spots. And that's what a full sky map means. Yeah. So here's just to show you, here's me in 1992, and here's George Smoot, and here's a differential radiometer, not too dissimilar from the one that was put on the Kobe satellite that made the map in the previous slide. Now, what is this radiation? Where did it come from? And how do you understand it? Well, I like to think about it. Here's a way to understand what the cosmic microwave background is. Think of a field, an infinite field full of people. So these are supposed to be people, these circles here. And imagine that everybody here has a watch, and everybody is screaming as loudly as they can. Ah! They have a watch and they're screaming. And then they're all going to stop screaming. So here you are in the center, and if you wait, everybody, you stop screaming, and then you wait a second. After a second, what will you hear? You will still hear all of these people screaming. Why? Because it takes sound. It's 330 meters a second. That's the velocity of sound. So this is 330 meters. And so it has taken a second to go from here to there. And so you still hear them screaming. As a matter of fact, everybody that is 330 meters away from you, you will still hear screaming even 1 second after you and everybody else has stopped screaming. What about 2 seconds? Well, 2 seconds, you will hear a surface of last screaming that's twice as far away. After 3 seconds, you will hear a surface of last screaming that is 1 kilometer away. So that's an important issue. So no matter how long you wait, you will always hear a surface of last screaming that is receding from you at the speed of sound. I hope that's clear. Does anybody have any questions about that? Oh, I'll wait 2 seconds, 1, 2, and then I'll continue. So now let's, instead of having people screaming, let's have the whole universe very, very hot, and then it becomes transparent. This is what happened about 380,000 years after the Big Bang. The universe cooled down. Electrons and protons formed atoms, and they were transparent, and so you could see for the first time. And so this the photons kept coming from the surface of last scattering. And now as we wait, this surface is moving away from us at the speed of light, not the speed of sound. Basically, that tells you that the microwave background, the Big Bang happened everywhere. It happened in the room you're in right now. The Big Bang happened in the room, but because you've waited 13.8 billion years, you can only see it happening at a surface of last scattering that is 13.8 billion light years in every single direction around you. And that is what this map is. Now, another way to think about that is the following. Here we have an observer in the middle. Here's the photosphere of the universe. That's what this is, a photosphere of the universe. If we had neutrino telescopes, we could look beyond the photosphere. And the reason this is a photosphere is for the same reason you cannot look into the sun. The sun has a surface. The reason you can't look into the sun is because the electrons and protons are scattering the light, and you cannot look into it. But after the light comes out of the sun, then it travels freely to you. The same thing happened here. The whole universe was hot and opaque, but then it cooled down, and then it became transparent, and then the photons coming to us from all these directions, and that's what we're seeing, a full sky map. If you had a neutrino telescope, then you could see beyond this photo. And for example, we can see inside the sun with a neutrino telescope. We can do the same thing with the universe. If we had very sensitive neutrino telescopes, more sensitive than we have today, and if we had really, really sensitive gravity telescopes, then we could see even further, really close to the Big Bang, when the temperature was 10 to the 32 Kelvin. That's very, very close to the Big Bang. Matter of fact, that's about the Planck time at 10 to the minus 43 seconds or so after the Big Bang. So I will stop there for any questions about this surface of last screaming, surface of last scattering. I think it's really important that you understand what it is that you're looking at when you see the most distant photons in every single direction. So any questions for me there? If not, I will continue. All right, I will continue. So what I've just talked about is the recession velocity of distant galaxies equals some constant times distance. So recession velocity is a constant times distance. Now, what's interesting about this equation is that if you go far enough, then this gets bigger and bigger and bigger, and you can have it equal to the speed of light. So so this can be the speed of light, and then there is a distance which makes things recede at the speed of light. And for all distances that are greater than this distance, we have a recession velocity greater than the speed of light. Now, you have probably been told that nothing can travel faster than the speed of light, but that's special relativity. I'm talking about general relativity and the expansion of the universe, and that allows to have recession velocities greater than the speed of light. The reason why that makes sense is because those distant galaxies are not really moving through space. They are at rest. And matter of fact, if they look at us, they think we are receding, but we are at rest. And so you can have two distant galaxies at rest, but they are receding at faster than the speed of light. Why? Because space is expanding. So if Hubble's law is true, the distant part of the universe are receding faster than light. Okay, now this brings up something that I call the paradox of the ubiquitous grapefruit. Now, one of the reasons I became a cosmologist is because of this paradox. So if you look back in this direction, as far as you can see, and you can look in that direction as far as you can see now the universe used to be smaller. And the further back in time you go, the smaller and smaller and smaller it gets. So we say, oh, there was a time in the early universe when the whole observable universe was the size of a grapefruit. You go even further, it's the size of an atom. You go even further, it's even smaller. But there was a time in the early universe when the whole observable universe was the size of the grapefruit. And the paradox is, you can see the grapefruit if you look in that direction, and you can see the grapefruit if you can look in that direction. You're seeing the same grapefruit. That's why I call it the ubiquitous grapefruit. So one way to understand that is, here's how you can understand that. So time is going up here, and here's us now. Here's now, and here's all space. So space is one-dimensional, not three-dimensional, not two-dimensional, but one-dimensional. And here's the past. Here's where we were like 1 billion years ago. Here's 10 billion years ago. Here's where we were 13.8 billion years ago when this radiation was given off, and we gave off that radiation too. But the radiation we gave off went this way and that way and is not affecting us here. The radiation given off here came to us, and the radiation given off here came to us here. That's why this is called a past light cone, the photons coming to us here. Now, so this map is right here. Actually, it's the 1 point here and 1 point here. But let's see. Now, this line here is the redshift of about 1,000. I'm not sure if you know about redshift, but the more distant a galaxy is, the higher its redshift. And if you look at for example, the deep field from the James Webb Space Telescope, they look at galaxies that are redshift of 5 or 8 or 10 or 12. Well, this radiation is at a redshift of 1,000. And at a redshift of 1,000, the observable universe was 1,000 times smaller than it is today. And even earlier, the observable universe was smaller, even smaller than that. So that's why we can say that we look in this direction, and we see this grapefruit, this very, very small observable universe, and we look in this direction, and we see the same grapefruit. How can you have a grapefruit here and the grapefruit there being the same? And that's the paradox. And now I'm going to resolve this paradox. But first I have to tell you that anytime you see a past light cone like this, if you have a cone-shaped past light cone, the expansion of the universe has been taken out of the diagram. So there's no expansion. That means that a galaxy here just goes straight up in this diagram, and a galaxy here just goes straight up in this. If this is a galaxy that we're seeing, then today it's here. We can't see it. We're here. This one has gone straight up. Today it's here. We can't see it, but we can see it when it gave off radiation right here. Okay. If this is not clear, please interrupt me. Please interrupt me. I know I'm speaking fast and I'm talking about some weird concepts, but that's more or less the point. So please ask questions if you have any. Now notice that in this diagram, we have a cone-shaped past light cone. Now watch this. Now I'm going to draw a diagram. This is a diagram with a teardrop-shaped past light cone. And the expansion of the universe is included in this diagram. So here's distance. Here we are today. Here's 10 gigalight years, 20 gigalight years. And galaxies that are redshift 1 go on this path here. You can see they're moving away from us. A redshift 3 galaxy goes from here to here to here. It's moving away. And our past light cone, instead of being a cone, is a teardrop shape. And that's the key to the solution of seeing the same grapefruit in different directions. So if you're interested in this, I can recommend this paper, Davis and Lineweaver 2004, called Expanding Confusion, Common Misconceptions of Cosmological Horizons and the Superluminal Expansion of the Universe. So this is a diagram of us. Here we are right now. So that's us right now. And when we look in that direction, we're looking along this line. And when we look in that direction, we're looking in the opposite direction along that line. Light is coming to us from here, and light is coming out to us from here. Now, what's really it's interesting. The scale factor, that means the size of the universe. Now, the scale factor is just a number we use to define how big the universe is, and we arbitrarily set it to be 1 today. And you can see over here is time, and here's 13.8 billion years today, right now. That's why it's called now. So the whole universe now is on this blue line. But the part of the universe we can see is along this red line. That's where photons are coming to us. So us now, when we look in that direction, we're coming photons from here. When we look in that direction, it's from the opposite direction. Now, how is it that we have a teardrop-shaped light cone? Well, that's because when you have it far enough away, there are galaxies that are far enough away, they are receding from us at the speed of light. And when that's the case, the light they emit to us is not being able to come closer. That's what happens when you're right here at this Hubble sphere. Hubble sphere is defined on this line as moving away from us at the speed of light. So you see the fattest part of the light cone right here and right here? Well, that was at a time of about 4 billion years after the Big Bang. And it has the universe was a factor of 40% of what its size is today. But the scale factor of the microwave background was about 1,000th, 0.001. And that's where this red line is, just above the Big Bang, which is right here. So now the reason I went to the detail of showing you this teardrop-shaped light cone and how long ago this fattest turnaround point is because if you look at an illustrated version of Stephen Hawking's work, you will see a light cone that looks like this. And here's we are today. It's teardrop shaped, so that's good. But look, they put the microwave background right here. And instead, it should be down here. As you can see in this diagram here, you can see the red line is really at the bottom of this teardrop. And yet the artist put it up here. So it's really wrong, really misleading, at least for somebody who pays attention to some of these details of illustrations in popular science books. Okay, so that's where that microwave background radiation does come from when the universe was 1,000th the size that it is today. So I've been talking to you for about almost half an hour about, well, not half an hour, I'm not sure how long it is. Anyway, what does it mean to have the universe is expanding? Now, that is a difficult concept, and I've tried to talk about it in a way using past light cones. Again, I'm going to stop to see if there are any questions. I'll wait about a minute while I drink some water. Sukata, no questions there?
No, I'm not seeing any in chat, and I just checked YouTube chat as well, and I'm not seeing any
Okay.
there yet.
Okay, I will continue then.
That's a little behind of the Zoom, so maybe people are catching up there. But if they put any questions in the chat channel, I'll definitely respond to you.
I feel like I've been talking too quickly, and maybe these concepts are so weird or so different that maybe people say, "Oh, I have no idea what he's talking about," and that's why I'm a little bit afraid of.
Don't worry about it. I mean, people will ask for clarification if that's the case. So, yeah.
But anyway, there's room for questions at the end. So I've talked about what implications of what it means to have a universe that is expanding. But now I want to talk about, well, is the universe infinite? Is the universe spatially infinite or not? All right. So according to general relativity, there are three possibilities for the topology or the shape of the universe, the shape of space. One is the universe could be like a ball with positive curvature. And that is, if you send a light signal in one direction, it goes back, comes around and hits you in the back of the head. That's what positive curvature means, that the universe is shaped like this. It could be that the universe has negative curvature, in which case it's shaped like a saddle. I should point out that, or it could be a table and flat curvature. And the answer seems to be flat. And one implication of that is a triangle has 180 degrees inside of it. Here, the interior angles of a triangle add up to less than 180 degrees. And here they add up to more than 180 degrees. And that's one way, that's a test we use to try to figure out what the topology or the shape of space is. And the answer is, it comes from the microwave background again. And while we were making the microwave background, there are two parameters that can be derived from the incredibly rich data set of the cosmic microwave background, fluctuations as a function of size. So in this plot, this is omega m. That's just a fancy way of saying how much matter is in the universe and how much, this is the cosmological constant, how much vacuum energy is in the universe. And when you plot this like this, you can say that up here in this region here, it's closed and finite, like a surface of a sphere. Surface of the Earth is like a ball. It's closed. There are no boundaries to it, but it's also finite. And if we go down here in the open region, then we have negative curvature and it's infinite, like a saddle, just goes on like a saddle. It's shaped like a saddle. But there's a third possibility, and that is right in the middle is on this, if you're exactly on that line, then the universe is flat, kind of like this table here. And there are 180 degrees in the interior angles of a triangle. And so since we can derive these two parameters from the cosmic microwave background and about 6 other types of cosmological observations, the answer comes in as that's where we find the universe lives in this plot right here. So it's very consistent with being flat. Of course, there are error bars. So you could say, well, it still could be open, still could be closed. But increasingly, the error bars are getting smaller and smaller, and they're staying consistent with being flat. And why that's important is if the universe is topologically flat, like a table, that means it goes on forever in every direction. That means we have an infinite universe. So that word infinite here applies not just to open, but to flat case. Finite is over on this side of that line. So observational constraints seem to suggest very strongly that the universe is flat and therefore infinite, spatially infinite. Now, what does that mean? If in an infinite universe, I've heard this several times, in an infinite universe, everything that can happen will happen an infinite number of times. Now, that's an interesting statement. And I said, well, isn't everything that can happen, isn't everything that has happened, isn't that possible that it can happen? And therefore, there will be an infinite number of me, an infinite number of yous, an infinite number of everything, an infinite number of your dog named Dilly, for example. Well, here's Tony Abbott. He was the Prime Minister of Australia from 2013 to 2015. And he's famous for having said, nobody is the suppository of all wisdom. So let's talk about how many Tony Abbots are in the universe. What is the probability of Tony Abbott? So here's the probability of Tony Abbott. What is it? Well, let's suppose that the probability of Tony Abbott is epsilon, a very small number, and that the universe is spatially infinite. Epsilon times infinity equals infinity. So therefore, there are an infinite number of Tony Abbotts in the universe, but there are an infinite number of me's or an infinite number of anybody else in the universe. Why? Because the probability is, although it's a very, 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 very small number, it's still non-zero. And then when you multiply it times affinity, you get infinity. That is the reasoning for why there might be an infinite number of Sukhatas in the universe. Now, most people are not happy with that, but there is a way out. There's a caveat. What if the probability of Tony Abbott is zero? If the probability of Tony Abbott is a set of measures zero, then instead of this epsilon times infinity, you make 0 times infinity. And then when you multiply that, you use not necessarily infinity. Maybe it turns out to be 1. I'm not sure. You'd have to ask a mathematician what 0 times infinity would be, and he would say that doesn't make any sense. But as a physicist, we tried to ignore mathematically rigorous definitions like that. But anyway, one way of getting out of this conclusion is to say that the probability of any particular person is a set of measures 0. Now, in an infinite universe, the only thing that protects us from an infinite number of Tony Abbotts is the idea that he is a set of measures 0. Now, what is a set of measures 0? One way to understand that is if you take the real number line and the rational numbers are embedded in the real numbers, let's say between 0 and 1. And there are an infinite number of rational numbers between 0 and 1, and there are an infinite number of real numbers in the same region between 0 and 1. But we now know that the numbers of real numbers is much, much larger. The infinity of real numbers in this interval from 0 to 1 is larger than the infinity of rationals. And this is something that was developed earlier on, about 100 years ago. So but we want to ask the question, what kind of infinity is the spatial infinity of the universe? And this is George Cantor, who is kind of like the father of different kinds of infinity. And he said, infinite sets are not all the same size. The rational numbers are countable, the real numbers are uncountable. Therefore, the infinity associated with real numbers is larger than the infinity associated with rational numbers. Well, that's kind of interesting. There's also another theorem that says for a set A, the size of this set of all possible subsets is larger than the size of A, even when A is infinite. So what that means is, let's think of the natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there's a set of all subsets of that would be 1 and 2, 1 and 3, 1 and 4, 1 and 5, and then 1 and 15, and 15 and 7. And those are all possible subsets of the natural numbers. And that set of all possible subsets is an even larger infinity than the natural numbers. I know this is quick, but this is the reason why that's interesting is because we're trying to figure out if the universe is spatially infinite, what kind of infinity is it? You can't just say infinite and then leave it at that, because we know that there are different kinds of infinity. So, for example, you could ask, should we expect humanoid aliens? Well, the answer to that surely depends on how big is the infinity of biological evolution. If you think it's very small, then hey, then the probability is epsilon. Infinity times epsilon is infinity. There's an infinite number of humanoid aliens in the universe. That's how you can wave your hands and apply these philosophical, slightly speculative versions of what we think we know about infinity to trying to figure out whether we should expect humanoid aliens or not. Drink of water, pause. Question, pause, if there are any.
Yeah, hi, Charlie. So Alex has a question in the chat. He's asking if the U is flat, is it not on the borderline between being infinite and finite? How does that say that U is actually infinite?
Well, any measurement will always give you a finite size region where the universe lies. And it used to be very big. And as we've made progress, we've decreased the size of this observation by maybe a factor of 10. So it used to be somewhere here, then it was somewhere here, now it's somewhere here, and maybe in about 10 years, it'll be like 1/4 the size. And every time it gets smaller, it's staying consistent with being on the flat line. So, and if it's on the flat line, it has this shape, and this shape just goes on forever, like a flat table. If it's like a saddle, if it's on this side, it's also infinite. But if it's just the least little bit above that line, then it's closed. But I should say the closer you are to this line, the bigger the ball. So notice that this ball is at a certain size. If you're right here, the ball gets bigger. You get closer here, the ball gets bigger. And if you have an infinitely large ball, it's essentially indistinguishable from a flat line. And that's why this is not just a sharp cutoff, but rather a ball gets bigger and bigger and bigger, bigger and bigger. And then it gets to be infinite sized here. And from here on, it's infinite. Does that answer the question?
Yes, that will do. Thank you very much.
Okay. But this is something we're trying to make progress. And for example, it could be possible that if this gets smaller and smaller, it goes over here, it goes over here, and then it will tell us how big this closed universe is. It's not just the fact of being closed, it tells us how big it is. Okay. Tony Abbott and different kinds of infinity with George Cantor. Now, if the universe is infinite and we go back in time, well, how can you have, and we have to have an origin of this universe. How can an infinite universe have an origin? Because for some reason, when you think of the word origin, you think of it as a certain point in space somehow, but you have to get rid of that notion and have to try to conceive of an infinite universe that is, as you go back into the past, gets smaller and smaller and smaller, but it's still infinite. Another way to say that is, if you take the number line between 0 and 1 and 2 and 3 and -1, it's an infinite number line. And then you squash it down, divide it, squash it by a factor of 2, squash it by a factor of 1,000, squash it by a factor of 1,000,000, you're still going to have an infinite number line. And that's the nature, that's why we think that down here, the universe was infinite. But this diagram is misleading because it's only showing us the size of our observable universe. And that's different from the entire universe. The observable universe is the part of the universe you can see. And the smart money is on the idea that that is only because we are here that creates this observable universe. We could be over here, we'd have a different observable universe, etc. So now we've talked about the universe expanding, and we've talked about, is the universe infinite? And we said, it looks like it's infinite and it's flat. But how can you have an origin from nothing? So let's again talk about the origin of the universe from nothing. And notice that the universe is expanding is in quotes, infinite should be in quotes, and then this nothing is in quotes. So what do we mean by nothing? Well, if you talk to philosophers like Plato and Aristotle, they have an idea of nothing, and it says, oh, there's nothing there. It's like the vacuum that has nothing in it. But the nothing of modern physics is not the nothing of philosophy. This is an important idea that you have to get into your head, because you've been told, you thought you knew what nothing is, but I'm here to tell you that modern physics tells you that there's no such thing as the nothing of philosophy, because when you get rid of, here's some space, you get rid of all the air, all the sound, all the light, you do not have nothing really, or rather, if you're going to call that nothing, that's got a lot of structure. It has irreducible quantum fluctuations. It's the modern physics vacuum, and there's no such thing as the pure nothing of philosophy. So when that's what, it's a little bit ambiguous here, but for a physicist, it's not ambiguous. But I think you should take this word nothing said by the philosophers and get rid of it, remove it from your head, because it doesn't exist. There is no such thing as the nothing of philosophy. If you want to talk about the pure vacuum where there's nothing in it, you have to talk about modern physics, and there's lots and lots of stuff in the vacuum of modern physics that cannot be removed by some thought experiment. So if you're interested in this topic, this is kind of like the basis of this book, A Universe from Nothing by my colleague Lawrence Krauss. And I can recommend it if you're interested in how in the world can you have a universe coming from nothing? Well, that's this book. And the secret to understanding that is the nothing here is the nothing of modern physics, not the nothing of philosophy or religion. That nothing does not exist. It's a figment of your imagination that has been hammered into you from the, oh, nothing is the absence of everything. Well, here's a picture of nothing in modern physics. It's these irreducible quantum fluctuations. So here might be our universe coming out of these irreducible quantum fluctuations, and then it gets bigger and bigger and bigger. And the Heisenberg uncertainty relations are the physics behind this irreducible fluctuations. And so what if you ask a physicist, what is nothing? They will talk to you about the Heisenberg uncertainty principle. They'll talk to you about irreducible quantum fluctuations. They'll talk to you about zero-point energy of the vacuum and polarization of the vacuum. And these things you can measure with the Casimir effect, the Lamb shift, dark energy, Hawking radiation, and Davies-Unruh radiation. And let me try to explain what that means. If you have an electron and you have some type of they have a thing that can be polarized, plus and minus, then this electron will attract the plus end and repel the minus end. So if you have an electron sitting in space, then and surrounded by other material, it will attract. For example, this could be water, H2O. H2O is a polar molecule, and so the plus end would be attracted by a negative charge. And also the same with all the other. Now, what that does is it shields this negative charge, and so the charge seen from outside is much less. So there's something called the Lamb shift. I know this is a little technical, but this was discovered in 1948. And what happens is this: you have a proton, and then you have electrons, virtual electron-positron pairs coming into existence, and they get polarized and shield this charge so that the bare charge of the proton is larger than the effective charge, which you see from farther away. Why that difference? Because these virtual particle pairs are being polarized so that the negative is here, the positive is here, negative is here, positive is here. The proton's bare charge is being shielded, so far away you see the effective charge. And this can be measured. It's called the Lamb shift. Another feature of the vacuum polarization is it's called the Schwinger effect. So that's a capacitor plate. Here you have a capacitor plate, let's say a metal plate that's positively charged, a metal plate that's negatively charged. And if you turn up the voltage between these two, what happens to these virtual particles that are being created? You pull them apart. You pull the positive this direction, you pull the negative that direction, and you end up ripping apart the vacuum. That's what it says. High voltage difference polarizes the vacuum and rips the vacuum apart. And this has been measured. There's also a Casimir plate thing effect that also creates boundary conditions in which long wavelengths cannot be created, and that creates a force. It's called the Casimir force. So what I'm talking to you is about, these are effects that are measurable of the irreducible fluctuations in the vacuum. And those are important because they become more and more important in the beginning of the universe. So here's another question you can ask: the Big Bang. What caused the Big Bang? And here's one answer to that. If we're going to talk about the Big Bang, we have to talk about quantum cosmology. And in quantum mechanics, if you have, let's say this is the nucleus of a uranium atom, and we know that uranium decays, but quantum mechanics tells us that the decay of a uranium nucleus can only be described statistically. That means we can say, oh, its half-life is, a billion years or so. That means if you have a bunch of it, after a billion years, half will be decayed. But there's no way in principle, supposedly, of looking in detail at some hidden variable inside the nucleus and saying, it's about to decay. Oh, now it will decay. Rather, the worldview of quantum mechanics is that we can only describe this statistically. So similarly, if the Big Bang in quantum cosmology describes the Big Bang, then it too has to be described statistically, and we don't have a cause in the same way that you don't have a cause for the decay of the nucleus of a uranium atom. Another philosophical question is, why is there something rather than nothing? And if you look at Ricky Gervais and Stephen Colbert, they debated this for about a minute on Colbert's show. And I think the answer to that question is, why do you think nothing is more fundamental than something? Obviously, there's something in the universe. If you're asking this question, you say, wait a minute, nothing is more fundamental than something, so it should be nothing. And so you ask that question. So I would say, I don't think that nothing is more fundamental. Something seems to be more fundamental. I know that's a little bit of a semantic, it sounds like a semantic game, but I don't think it is. And we'll move on. What happened before the Big Bang? Well, here we have, in high school, you have time and space. But if you go back to an earlier universe, you get time and space we know from general relativity can be curved. And that's what this looks like. If you go back even earlier, it gets even more curved. And if you go back even earlier to the Planck time, then you have something that's probably like space-time foam. And by looking at this diagram, it's hard to ask the question, what happened before the Big Bang? In this diagram, before is down here somewhere. But in this diagram, I don't know where before is or future. So this is what happens to space and time. They get all mixed up and all curved when you get closer and closer to the Big Bang. Now, to finish up here, Steven Weinberg wrote a book called The First 3 Minutes, and he wrote, the more the universe seems comprehensible, the more it also seems pointless. And so here we have Copernicus and Darwin and Freud and materialism and anonymity. We live in an average galaxy, and then maybe even our universe is part of a multiverse. And the more the universe seems comprehensible, the more it also seems pointless. It's dethronement, humiliation, and loss of hope for humanity. But there's another way to interpret the same thing, and that is, look at all the progress we're making in understanding our place in the universe. We've understood that the Earth goes around the sun. We've understood that we're an animal and have evolved. We're understood that, hey, what we're thinking is only a tiny fraction of what's going on in our brain. And we learned that materialistic reductionism can explain a lot. And then we learned that our galaxy is part of many, many galaxies. And isn't it wonderful that we can understand this context in which we exist? So here's a list. This is just a summary of what I've gone through. I know it's a long list of weird ideas. And again, if you want to have a look in this, dip your fingers in a little bit more, I suggest this book here by E.R. Harrison. He's one of my cosmology heroes because he includes so much philosophy in his cosmology. And here's a quote from him. I'll leave you with a quote. He said, "Every generation believes they have at last figured out the true nature of the universe." So I'm finished. Thank you very much. And I'm prepared for questions. I hope there are some.
Thank you so much. I mean, that has given a lot of food for thought, blending philosophy with cosmology. I've never thought of it that way. So with that, the floor is open for questions. If you want to unmute yourselves and ask your question or put it in the chat, if you're feeling shy, that's fine too. But yep, let's start the Q&A. Everyone is very quiet. I have a not exactly related to today's talk question. What got you interested in this blend of cosmology and philosophy?
I've always had it. I guess one of the you could say that, why did you study cosmology? I studied cosmology because when I was studying astronomy, there were so many details, and cosmology seemed easier because you're talking about one object, the entire universe, and you get to ask questions about almost, well, there are definitely philosophical questions like, how did the universe begin? Where did it all come from? These are very deep questions that appealed to me, and so that's why I studied cosmology. So it's as if I had a philosophical curiosity, and then I found some answers in cosmology about the origin of the universe and about what the vacuum is and what nothing is, and whether questions like, why is there something rather than nothing? As soon as I heard that question, why is there something rather than nothing? I said, that's a stupid question. Why do you think nothing is more fundamental? So it really, a lot of these questions depend on your assumptions. And when you ask, why is there something rather than nothing? In the back of your head, you're assuming that if nothing existed, then you wouldn't need an explanation. But that's kind of crazy, because you can't have an observer in a state where there's nothing. So there has to be something. And the vacuum of modern physics tells you that there's no such thing as the philosopher's nothing. The vacuum, if I know that most people have this, oh, I know what nothing is, it's nothing. Well, no, wrong. Sounds so simple and so right, but it's wrong, because we physicists know what the vacuum is, and it's full of stuff that you can't get rid of. And so get rid of the idea of the philosopher's nothing from your head, and you can make a lot of progress.
Mm-hmm. Well, Karthik has a question. How can high school and university students get involved with this field?
Read this book.
Edward Harrison. I have read the first 3 minutes, and that was very, very interesting read.
Yes.
Definitely.
Weinberg, unfortunately, Weinberg just died recently, but he's a very excellent physicist who got the Nobel Prize. And so anything he writes, I can recommend.
Yep.
He's also written much on the relationship between religion and science. But the first 3 minutes is certainly something. Here, I have a couple of books here. Here, I have my Stephen. Here's my Stephen Weinberg collection. He has another cosmology book that's kind of difficult, though. The Harrison book is much better. Here is his earlier book called Gravitation and Cosmology. Here he's also written To Explain the World. So that's a book that is full of essays that are more accessible to people who don't know what equations are. And here he also has a book called Third Thoughts. He's one of my heroes. He's very straightforward and not mystical and very scientific. So
I think that's one thing I liked about this book. He has explained everything at maybe at high school level. So if you don't have a lot of background in physics or math, you can still follow along.
Yeah, these two books are like that, and these two books are definitely not like that.
I see somebody has raised a hand. Oh, Sam, do you have a question, Sam?
Yeah, well, just one quick observation. There was a blog post of a guy named what's his name? The blog is better known. It's called Not Even Wrong, last month. And there were some really, what can I say, strange details about how Weinberg, Glashow, and Salam, and the jockeying that went on for the Nobel Prize. And I'll just add a link to it. It's
okay.
Oh God, the politics of it is really bad, and none of them comes out of it looking very good, except maybe Glashow.
Interesting. Well, I'm not part of the community.
Getting a Nobel Prize is a political thing almost as much as a scientific thing, and that's kind of the same thing you could be said about almost every Nobel Prize, and that is, did this guy really deserve it? Or wait a minute, he had a collaborator. How about the collaborator? And wait a minute, there's a whole team behind this guy. So that's the almost impossible task of the Nobel Prize committee, is to figure out which 1, 2, or 3 people are responsible for this particular discovery. And the real answer is there are many people involved in almost every discovery.
Yeah.
I have a question, if it's okay. I have heard that, I believe it's in the microwave background, that there may be evidence of the collisions of universes. If universes are infinite, how do they avoid colliding with each other?
Right. Okay. So that evidence comes from Penrose. Now, Penrose, matter of fact, I have 4 books by Penrose over there. I think he is a very, very good mathematical physicist, but he's not a very good data analyst. And about 6 years ago, he presented some of these ideas about looking for structure in the microwave background, and he was claiming that there was, but all of my friends and anybody else who had deep understanding of how complicated the data set was suggested that these were systematic errors that they were misinterpreting. And as a matter of fact, over the past 20 years, there's a big, I guess there are minor controversies about, oh, look at this effect in the microwave background, look at this effect, look at this effect. And in order to analyze these effects and what the theoretical predictions are, you need to be very, very deeply involved in the data analysis. And I'm afraid that Penrose and the people who he's using to analyze the data were not as good as the best experts. And the opinion of the best experts was that what they were seeing was not what they weren't seeing, what they thought they were seeing. And so that's why, although maybe I'm wrong about that, but because you could always be wrong, but let's just say that the theorists that I've run into are not very good at doing data analysis, and Penrose is like that. But Penrose I admire incredibly for his work on the entropy of the universe. That's something I didn't get to talk about, and that is the entropy. The early universe had to be very, very, very low entropy to get started, but the microwave background is black body radiation, which is maximum entropy. So there has to be some solution to this problem of the universe has to be low entropy to make anything happen. But we see it in observations of the microwave background is the maximum entropy. What's going on? Those two things are completely opposite. And the solution seems to be one that Penrose has proposed, not in detail, but the proposal is that there's something called gravitational entropy, which is very, very, very low, and that compensates for the high entropy of the microwave background radiation.
The other part of the question is if all these universes are infinite in extent, how do they avoid colliding with each other?
Well, that is remember I said that in general relativity, there's no space outside the universe to expand into. And so if you're talking about a universe that's expanding, let's think of it as a two-dimensional trampoline that's infinite. And this two-dimensional trampoline is expanding. Now, your question assumes that the other universes are in the same space, but just beyond this universe. That's what the question assumes. But if the other universes are in another universe, they don't overlap at all. So you have to be careful about what you're talking about. For example, if you're talking about an observable universe here and an observable universe over here, then they can overlap. But if you're talking about disconnected universes in a multiverse scenario, then they don't necessarily have to overlap. So we're not quite sure what the structure of this multiverse is. We do know it. I think we do know that if our universe is spatially infinite, let's call that the entire universe. Our observable universe is a subset of that, and we can have observers way off in our universe, our entire universe, but outside of our observable universe. Or you can have a whole different universe that is not part of our universe, and then you wouldn't have collapse or collisions, even if, no matter how big either one of those universes gets. So these are questions we don't really know the answer to, but don't necessarily assume that these other universes are part of a space in which it can collide with another universe. I should point out, however, that Steinhardt and Turok are talking about colliding universes all the time, and I'm not quite sure what they mean, and I don't know if they are either.
See, I'm gonna check the YouTube channel once, and then I think Shanjoy asked a question in the chat channel. Can the universe have a beginning? Is there an end, or can it be eternal?
So repeat the question, please.
Oh, sorry. Let me open the chat again. Can the universe have a beginning? Is there an end, or can it be eternal?
Okay. Well, the idea of having an eternal universe, one problem with that, for example, they have the Hindu philosophy has the universe bouncing, getting bigger and bouncing, and it's very long and it's just eternal. And the problem with that from the point of view of modern science is entropy. Entropy is always increasing. And you cannot have a minimization of entropy. It increases, it stays the same or it increases. That's the only law we have that is not an equality sign. It's a greater than or equal to sign in that law of increasing entropy. So if the universe were eternal, then we would be at the end of an eternity, in which case the entropy of the universe would be maximum. And then we wouldn't be able to talk, where the sun wouldn't be burning any hydrogen. All the stars will have burned out all the hydrogen, and there will be no gradients, no thermal gradients. Everything would be in equilibrium, and everything would be dead. There's no room for life, because life requires gradients of free energy. So that means that the universe, any universe has to start out in low entropy. And if we are in the infinite future of a low entropy universe, we have to be at maximum entropy, which is obviously not the case. So the past infinity idea doesn't float unless you can think of a way to reduce the entropy on a global scale. As to the future of the universe, well, the universe is increasing its entropy. The sun, for example, is burning. I can see the sunshine right now. It's turning hydrogen into helium and then helium into carbon and oxygen later on. And all the stars are doing that. In the far, far, far future, there will be no gas in the tank left, and the universe will get cooler and cooler and cooler. The universe is expanding rapidly. It's cooling rapidly. So, for example, that the 2.7 Kelvin background radiation is going down to 2, then it'll go down to 1, then it'll go down to 0.1, then it'll go down. The universe is getting cooler and cooler. And so we will have what's called a heat death, which is a little bit of a misnomer because it should be called a cold death. And so the future of the universe looks, this is like hundreds of billions of years in the future. So the universe is cooling down. We will eventually get a heat death. There will be no more starlight, no more heat gradients, and life will be impossible. But as to the beginning of the universe, we think there was a beginning because of this expansion of the universe. And we extrapolate the expansion back in time. Everything gets closer and closer and closer, gets hotter and hotter and hotter. And if you read the first 3 minutes, you can read about what happened during the first 3 minutes. And it's a very, very dense, hot place. And if you go even earlier, then it gets even denser and hotter. And then we have something called inflation, which we have to invoke to understand some of what we see today, but that is very speculative, and lots of people are working on it, and I'll stop.
Well, I hope that answered the question that Chandra had. I'm not seeing any new questions coming in the chat.
Sure. Something that's been bothering me, which is partly philosophical and partly scientific, which is how should credit be given for ideas that may have had a very nebulous, no pun intended, origin, but they were really guesswork. And it is only with modern science that in the last century that people got a better handle on some ideas. So, for example, Immanuel Kant, he thought there might be some island universes, and in some way, shape, or form, he was guessing at the possibility that things like galaxies might exist. But it's only about 100 years ago that we actually managed to get a better handle on that idea. But so the question being, like, how should credit be apportioned in that type of situation? And secondly, there's a real world kind of impact of this type of priority of whatever you want to call it, discovery, in terms of there are some parts of the world where there's some very nasty politics that goes on. And there are some politicians who will claim that, well, our culture, quote unquote, had discovered this idea long ago. And so, yeah, things can get very chauvinistic, and yeah, you can get into some really, again, dangerous political currents. So just curious, sorry for a rambling question. Thanks.
Well, let me say a few words about that. It's almost the difference between theoretical physicists and observational physicists or experimental physicists. Theorists can come up with an idea every day. They can say, oh, there are galaxies, oh, there are non-galaxies, oh, there are this type of things. In other words, as a theorist, your job is to come up with ideas and not necessarily test those ideas. That's the job of a theoretic of an observer or an experimental physicist. In the microwave background, there's an excellent example of this, and that is there were two radio astronomers, Penzias and Wilson, who had this nice new telescope, and they were seeing a noise in it, and they didn't know what the noise was. And they tried to get rid of it and tried to get rid of it. They thought it was pigeon poo. They thought it was this, or maybe it was interference, but they didn't know what to do. And then a guy named Dickey at Princeton University heard about this noise, and he said, well, that's what I think is from the theory that I have of this Big Bang, that the universe used to be hot, and what you're seeing is the universe, the cosmic microwave background radiation. Now, the Nobel Committee has, you don't get a Nobel Prize for being a theorist. You get it for being more substantial, being more specific, being more exact, of seeing something specific with an instrument. You're measuring something. And theorists don't measure something, they have these ideas. So Dickey's idea was, you're looking at the microwave background radiation. Penzias and Wilson published saying, here's the noise, and by the way, Dickey has an idea about what it is. It's the microwave background radiation. The Nobel Prize didn't go to Dickey, the theorist, who knew what they were seeing. The Nobel Prize went to the guys who discovered the noise that didn't have any other explanation. And that seems kind of backwards, because Dickey knew what was going on and they didn't, but they were the ones who measured something. And that seems to be the way that the Nobel Prize Committee is all about. For example, Hawking came up with the idea of Hawking radiation. He was a theorist. He didn't get a Nobel Prize. But if his Hawking radiation had been discovered, it hasn't been discovered yet. Everybody thinks it's there, but it hadn't been discovered yet. Then if it were discovered during his lifetime, then he would have gotten a Nobel Prize despite being a theorist, because he came up with this idea, very specific idea. So I don't know. I wouldn't take the idea of credit too seriously, but there are a lot of good scientists working all over the place. And one of the questions that you talked about could have religious implications, because as a cosmologist, I'm always running into people who said, oh, in the Bible talks about, the Bible predicted that, or the Quran predicted that, or the Bhagavad Gita predicted that. And they say, we knew about this before. And basically there's some guru on the top of every mountain who has already predicted what you are seeing specifically. And the problem with that is that the Bible and the Quran and the Bhagavad Gita and many other holy books say all kinds of things in a very vague, metaphorical way. And then when something specific is found by modern science, they say, oh, we predicted that. And the answer is, no, you didn't. If you're waving your hands in every single direction, metaphorically, then you predict essentially everything that could be detected later on. And so those claims of religious claims of having found the truths of modern physics before the physicists did, I don't put much credence in.
Right, that was an interesting question, but I think that was probably the last question for the night. So thank you so much, Charlie, for joining us from all the way down under. And this was fantastic. We should probably do this again sometime. And if anybody has any other follow-on questions, you can probably send me an email and I can pass them on, and we can get them answered that way. All right. Thank you so much, everyone, for joining, and have a good night. And I'm going to stop streaming before I let you all go.
Thank you for inviting me.
Yeah,
bye-bye.
End the stream here.